Hey, welcome everyone. Today we're happy to have Justin Kulp from Stony Brook. We'll talk about do null defects dream of conformal symmetry.
Yes. Okay, yeah, so thanks a lot for having me here. It's very nice. It's my first time in Chicago. What I wanted to tell everybody about was this project, indeed, with the title do null defects dream of conformal symmetry. It's this archive number. If I had more time, I would have drawn a QR code that you could have scanned, but that would have taken an inordinate amount of time. And with my collaborators, Rajiv Aramili, who's a postdoc at IHES, and Fedor Popov, who's a postdoc at Simon Center. That's the outline of the talk, but I'll come back to that after a little bit of introduction. The first thing I want to do is I just want to open up with some basic philosophy, like why do we care about defects, null defects, conformal symmetry, etc. This is all stuff I assume most people know from their classes on quantum field theory, but I come from a school of quantum field theory where we really think of quantum field theory as a really hard deformation theory problem. And this is sometimes very enlightening. So let me just tell you what I mean by that. So in particular, quantum field theories are characterized by their response to deformations, or their coupling to probes. Indeed, like every real observable in the lab, every bounded observable is a finite deformation of a quantum field theory by, I'm saying finite, I mean, it's kind of a redundant term, by some finite amount in some finite amount of spacetime, or possibly all of spacetime. But the point is, it's really a deformation of like a finite strength, as opposed to something like a local operator, which is a deformation in an arbitrarily small patch of spacetime by an arbitrarily weak amount of deformation, right? Because you've linearized something in an exponential. So every bounded observable is a finite deformation, every real thing that you measure. Now, when you modify a theory, let's pretend you were in a scale invariant theory. You could have been in any type of theory you want with any type of symmetry. But when you modify the theory, you may or may not break some of the symmetries you had. You may or may not change what you had going on. So in particular, if you were in a scale invariant theory and you deformed by adding a term to, let's say, the action, so that's like adding in the path integral, that's like adding a term all the way up here, yeah? So if you deform by some finite amount up here in all of spacetime, then that's generically going to break conformal symmetry, or scale symmetry at least, and then there's going to be some RG flow, and essentially, it's sort of a vacuous point, the endpoints of those RG flows, if they exist, are also going to be scale invariant theories, and they're going to be different. And indeed, we think of essentially all quantum field theories as some RG flow between two fixed points. Not always, but you can grant that. Similarly, we can consider defects. These are modifications of spacetime on higher codimension surfaces. So just like usual deformations, when you modify the theory on a surface of a higher codimension, you're going to break some symmetries, and you're going to trigger some RG flow. So you could imagine I had some theory here, maybe it's conformal, maybe it's not, but I do some modification on a higher codimension thing, and I do an RG flow, and I can possibly flow to a defect CFT in the IR. And much the same way that CFTs model universality classes of quantum field theories or critical systems, defect CFTs describe universality classes of modified systems. And why do we care about defects at all? Well, defects are essentially, they describe impurities in UV or very heavy probe particles, right? So these are some basic versions of defects. What else are defects good for? I mean, in modern times, we think of all symmetries as being topological defects. They're good for providing border parameters, just discussing whether or not there's some sort of phase transition. They're super important observables, important for dualities like S-duality. So these are all nice points, and conformal field theories play a distinguished role in the space of quantum field theories. Now, any quantum field theory, and in particular any CFT, let's say, CFT, makes sense in Euclidean or Lorentzian signature. So, and these two pictures are, of course, related by Wick rotation, right? So you go between a Euclidean quantum field theory and a Lorentzian quantum field theory by Wick rotation. And we're all physicists in this room, so we all somewhat believe in Wick rotation. And this is a very useful picture because usually we think of Euclidean signature, not always, but usually we think of Euclidean signature as being much nicer than Lorentzian signature. In fact,
restricting to unitary theories.
Yes, today we'll only talk about unitary. I mean,
unitary Lorentz as Lorentzian in Lorentzian spacetime.
Unitary Lorentzian theories or reflection positive Euclidean theories. I mean, you could Wick rotate even if that wasn't the case, it just might not be useful. Yeah. But you know, usually we tell some story that we like to Wick rotate from Lorentzian to Euclidean because we like to say that, like, you know, e to the is becomes something like e to the minus is, or sorry, e to the minus s, and other fanciful stories. But yes, today I will only talk about unitary, quantum field theories. Great. Now, in fact, if you are a super mathematician and you are a little bit skeptical about Wick rotation or anything like that, you would even be still happy because there are very general theorems that say, for example, if you have a Lorentzian quantum field theory described in the Whiteman axioms, you have correlation functions of local operators in the Whiteman axioms, that you can equivalently reconstruct Euclidean correlation functions in the Osterwalder-Schrader axioms, or vice versa. So indeed, there are literal theorems that say these two quantum field theories should be equivalent. However, it's not guaranteed, so I'll say not guaranteed to be easy. So just because these two perspectives are equivalent, it's not obvious how you relate data in these two perspectives. As a concrete example, though, you know, Euclidean quantum field theory is still very useful. For example, if you're interested in what are so-called in-out correlators in the Lorentzian field theory, if you're interested in things that are time-ordered, for example. Another reason why Euclidean quantum field theory is really nice is because you could, for example, if you wanted to study some defect, you Wick rotate, and then all of your favorite tools from usual CFT, like radial quantization or something like that, still applies in the defect CFT. Like, for example, if I had my CFT, I can still pick some point, I can still slice it on balls, and then I can think of the Hilbert space as being supported on these spheres, and the spheres are just punctured by the 2 points. Okay, so why did I tell you all this? Well, one, because I care about defects, and two, because I'm very paranoid about Wick rotation. And it's not that I'm actually seriously concerned about Wick rotation. It's more just there are situations, like I said, where it's not guaranteed to be easy or simple how we relate these two pieces of information. So one very obvious place where these two things are not obviously connected is in, can people see this board? Or is this cut off by the lectern? I'm seeing lots of yeses. Okay. So one place where all of these problems sort of become very manifest, or a very intrinsically Lorentzian object, is a null defect in a Lorentzian CFT. It's not obvious to me, if you just have a null defect, there it is, along the null cone, what its analog is in Euclidean signature. Because if I was going to try and construct sort of the same object in Euclidean signature, well, I would try to put maybe the whole defect at just one point. It's very bizarre. So I expect that all information about null defects is contained in some Euclidean Wick rotated quantum field theory, but I just don't know what it is. So for the entirety of today's talk, I'm actually basically going to live entirely in Lorentzian signature. Now, you might say, do these null defects even exist? But I claim null defects should exist because, first of all, null Wilson lines have been extremely useful in our understanding of quantum field theory. So these are useful for understanding deep and elastic scattering, and in particular, a really nice observable with null Wilson lines is what happens when you bend or crimp a null Wilson line and you get some sort of cusp anomalous dimension associated to this bending. And this observable here, this cusp anomalous dimension, is very important again for deep and elastic scattering. A very physical consequence or application of this is in Bremsstrahlung problems, because this is basically telling you if you have a very fast moving charged particle, hits some material and it bends off at another angle, how much radiation radiates off. It's also very important for problems of soft radiation. So when you're describing soft radiation, you can usually resum all the soft radiation in one direction as some semi-infinite null Wilson line. Okay, so we care about null Wilson lines. Of course, these things are also very useful for our tests of ADS CFT or other things like that. If you don't care about high energy physics or ADS CFT, a null Wilson line should still exist in some material as an impurity moving at the local speed of sound in some system at criticality. And finally, they should exist if you've seen it all in recent years. There's been this interest in these objects that are called light ray operators or detector operators. And what a light ray operator or detector operator is, maybe I can give you a famous example of a light ray operator. A famous example of a light ray operator is this so-called ANEC. So I'll write it down. It's lim as r goes to infinity squared minus infinity plus infinity t 0 to 9 and I t and that dotted into. And what this observable does, basically, is you imagine you had some sort of super awesome particle event happening here, and it blasts off radiation, and it basically collects all of the radiation on this surface here at a radius r away, and then it pushes it out to infinity. So it's basically some sort of idealized detector or calorimeter or something like this. And these objects, these light ray operators or detector operators, have been super important in recent years for understanding the light cone OPE, the Lorentzian inversion formula. We've got new proofs of monotonicity theorems from these observables. And apparently our best measurement of alpha strong comes from using these detector operators. Is that true still? One of our best. One of our best understandings of alpha strong comes from using some of these detector operators in QCD. But you'll notice something about these detector operators is what they are is that you take at least some class of them, is taking a local operator and smearing it along some region, integrating it along some null line. But that, in the same sense that a local operator is not like a real proper observable in a quantum field theory, it's some idealization where you've just linearized some deformation of the action. A light ray operator is not really a proper bounded observable. If it's supposed to exist, then it should be in some sense a linearization of some proper defect, some finite defect. And does that make sense? Local operators only exist as idealizations. They're really idealizations of finite deformations. And a light ray operator is just, again, some idealization where you have a very weak deformation along a non-trivial, a surface of non-trivial codimension.
Do you morally expect this Lorentzian physics to actually all be captured in a Euclidean linearization of the space-time theory?
Well, yeah.
I mean, the asymptotic symmetry, I mean, you restricted non-compact space-times, presumably you're doing, then the asymptotic symmetry groups are not, it's not obviously where you see that data in the Euclideanization.
Yeah, I mean, that is why I say it's not guaranteed to be easy. I mean, I do.
I mean, is it guaranteed to be true?
Well, it's not obviously true, I agree. But again, we do know if you are like super mathematical, at least all the data of local correlation functions is contained in both. I mean, this is this theorem that says the Weidmann axioms are equivalent to Osterwald to Schrader.
Somehow, is that somehow effectively compactifying your space-time? So a compact Euclidean, a CFT on a compact Euclidean space versus when you're non-compact, there's asymptotic behavior that I wonder to what extent is actually guaranteed to be equivalent.
Yeah, I mean, if we just want to focus on CFTs though, even CFTs in Minkowski's signature don't really live in Punker in Minkowski space, right? They really.
Okay, so you're restricting. So okay, so not just QFTs, but
well, I will.
I mean, already Maxwell is not obviously.
Maxwell's conformal.
In for D,
Correct. Yeah.
not in other dimensions.
Okay, fine. So let's go to
Maxwell, even Maxwell in 4, the asymptotic symmetry group in Lorentzian signature. I don't know where you see that asymptotic symmetry group in the CFT.
Yeah.
There's a memory issue.
It's not,
Put it like that.
not guaranteed to be easy. Yeah. To
So
understand.
you think it's there somewhere? You could,
If it wasn't, that'd be super spectacular.
Yeah, I guess there's a question of where is memory in the Euclidean version of the theory. Maybe just taking you away from.
No. I mean, in some sense, you could say that's the entire point of this talk. Because the entire point of this talk, I mean, not that I'm going to answer it, but that's the entire motivation of what I meant here. Is that like if you imagined, I picked a really horrible situation, a null defect along the light cone, and it's not obvious what the analog of that is in Euclidean signature. That's equivalent to your question, right? Because by a conformal inversion, I can map the null cone to scry. And so then it's the same question. Yeah, and because I don't know how to answer that question, this entire talk is in Lorentzian signature. But we do know, for example, this fact that I keep bringing up is really important to people studying Lorentzian CFTs right now, because they know that if you take the OPE, correct me if I'm wrong, but they know that if you take the OPE of operators in Lorentzian signature, that you're forced to study these extended observables stretched along a null line. But if you're just looking at correlation functions of local operators, we know that it's the same as if you were studying correlation functions in a Euclidean CFT. So all the data is there.
Yeah, actually, I think the asymptotic symmetry group is actually hiding in these guys. Yeah, sure. So maybe I was asking a question that you're about to answer in some study of this. But
Yeah, I mean, I see the point too. I'm sorry for everyone else if this is a bit of a diversion, but yeah, I mean, in a CFT, you might reasonably hope that you could use some conformal transformation that maps a defect along the null cone out to scry, and then there's some algebra of the operators at scry which captures it. But yeah, I'm not going to do that sadly. So yeah, but you know, you are welcome to do it and you know, cite that paper. Or don't, but I appreciate it. Okay, anyway, yeah, so I really want to just prove that there are these pathological objects. Or maybe they're not pathological, but these somehow very Lorentzian objects, and I want to know if they actually exist. If they didn't exist, that would maybe be a good point to this question. So what do I mean by proving they exist? Well, to prove they exist, sorry, was everyone else happy, by the way, with my discussion of what I mean by, like, if a Lightlike operator, if these are supposed to exist, that they should be idealizations of some bigger operator? Like, so proving a null defect exists, a finite modification, would be a step towards proving these objects truly exist as observables. Everyone's okay with that philosophy?
I don't understand what you mean by exist. It means you can define without running to
I mean, yeah, so I mean, for a local operator is just an idealization of some bounded observable, right? Like when you're in the lab, you actually want to measure something. You literally take each interaction and like add it to your Hamiltonian, right? You probe it with some external system. And this is modifying it like at the level of e to the s plus something. And I'm saying a local operator is like a tangent, like it's like a linearization of this process. It's just it's an idealization. And so that's what I mean. Okay, so yeah, what do I mean by proving these things exist? So if I want to prove a defect exists, a Lightlike defect, what are some things I want to prove? You'll see I love lists. So I would like to show that they modify bulk correlation functions. Okay, I would like to show that they have good, maybe defect operators with a defect Hilbert space that exists. And I would obviously, by good here, I also mean like with bounded energy or something like that. And finally, I would like to claim that they're stable / they can end. So this is a very physical condition, right? I mean, if I turn on a light ray, or if I turn on a null defect, you could imagine I'm like firing some big laser or something like that. I want to make sure that it can actually end, because if it couldn't end, you could imagine that if you started it here, there are some ripples that go out like this and make your theory ill-defined in the far future, right? There's some runaway process. So we want to know if they can end. And we sort of initiate the program of understanding these questions for null defects in that paper. And these two things I won't really talk about today, but some of them are in the paper. I'm really just going to focus on this here, this question 1. Okay. And this whole program is really plagued with issues of like extremely subtle issues. Like, what do you mean? Like, there's all these Lightlike divergences everywhere. There's issues of locality, because if I said, oh, if you have some local operator on a defect, but the defect is null, and then I ask you what's the distance between these 2 points, it's 0. So even basic questions like what is the OPE of local operators on a defect is just total gibberish. So what I'd like to do today, I'm sorry I'm going a little slow, but I've already had so many good questions, is I'm going to talk a little bit about the kinematics of null lines. I'll talk about some abstract results. I'm just going to flash you guys some results. I'll talk about the 3+1D free scalar in depth. I'll take a weird detour into spaces of test functions. It sounds like a technical issue, but it's really where there's a whole bunch of deep things lurking. And then I will talk about the Leonard-Weichart problem of the massless of a massless charged particle, and these things I call perfect null polygons if there's time. In the paper, by the way, we're very systematic, but today I'm really just going to try and flash some results at you guys to give some insight into this like really complicated subject. And people can see this board, it's not blocked by the shadows of this. Thanks. Okay, so if there are no further questions about motivation or anything like that, or if there are, feel free to ask while I erase. I'm going to just tell you some facts about the kinematics of null lines. I guess I should have asked, how many people here are PhD students in this? Oh, that's spectacular. Okay. How many people are familiar with like conformal symmetries and all that kind of stuff? Okay, I should have asked how many people weren't. Okay, that's great. So lots of people are. So let me just talk a little bit briefly about the kinematics of null lines. Okay. I'm sorry for the messier. Okay, so in R1, D minus 1, the conformal algebra is SO2, D. Okay, and when you, this would be the conformal algebra describing a conformal field theory. And if I was to put in a timelike line, I won't talk about dynamics yet, I'll just talk about kinematics. An infinite timelike line, let's say it's along x1 equals x2 equals double dots, all the way to xd minus 1 is equal to 0. This is obviously the x naught direction. If I ask you just what symmetries does an infinite timelike line preserve inside this conformal? It preserves SL2R times SOD minus 1. The SL2R is spanned by P0D and K naught. And SOD minus 1 are just the rotations transverse to the defect. And so what this means in practice, if we were talking in practice, is it means like if you had a defect local operator or something like that, it's basically going to behave like a 1D primary with some transverse rotation indices. Okay, cool. And I'll just tell you this other fact is that the dimension of this group is equal to 3 plus D minus 1, D minus 2 over 2. Yeah. Okay, so now let's see what happens if I was to do this exact same exercise, but for a Lightlike defect. So if I was to put a Lightlike defect, my conventions are that my defect goes like this. So you could pretend this is along x plus is equal to 0. And then all of the, I'll use xi for all the other coordinates, xi, blah, blah, blah. And it's stretched along the x minus direction. Okay, oh, by the way, I've switched to light cone coordinates. Everyone's okay with light cone coordinates? Yeah, nice. All right, so I'm also going to introduce two other things. They're just useful, J0 and J0 bar. J0 will be D minus 1/2 m plus minus. And J0 bar will be D plus 1/2 m plus minus. These are just natural mixes of boosts and whatever the dichotomous creature. Then the symmetry group, the sub-algebra of the conformal algebra that's preserved by this infinite null line, it turns out is the following. It's this nasty creature here. I'll call it n subscript d. And it's this. It's SL2R times R times SO d minus 2 semi-direct product with a Heisenberg algebra. So let's talk about this a little bit in detail. So first, let me tell you what this J0 and J0 bar are. So what J0 is J0 is some sort of chiral light cone dilatation. So it leaves x plus untouched. It scales x minus by 2 powers of the scaling. This is a finite scaling. And it scales the transverse directions in the light plane outside of the board by 1 power. J0 bar is the same thing, but it scales the plus direction and leaves the x minus direction unchanged. Okay, and these two creatures live inside this SL2R. So this guy here, he acts non-trivially on the line, does dilatations in this chiral direction, like this. This J0 bar is this R factor here. It's sometimes also called the collinear twist. And this is an important quantity for people studying collider physics. So just to be clear, this SL2R is the analog of this SL2R. It has chiral D that lives inside of it. It has P minus symmetries along the line. And there's K plus symmetries that act as the special conformal that forms this SL2R pair. I don't like the way this board is. Okay. Just have to live with it. I'll just come over here. So you have this P minus symmetry, this J0, this K plus, and this SL2R. You still have an SOD minus 2 of rotations. These are the rotations in the light plane transverse to the defect. Yeah. And then finally, you have this mysterious part here that I call mapfrac H d minus 2. And this is some Heisenberg algebra. And what lives inside of it? H d minus 2 is equal to, so it's spanned by all the KIs, K minus, and M minus I. So in summary, these are all the things you've preserved. You preserved P minus, J0, K plus, J0 bar, MIJs, KI, K minus, and m minus I. I call it a Heisenberg algebra, by the way, because the commutator of ki and m minus I commutes to ki, or k minus, which is a lot like what happens if you have x hat, p hat, and 1. Yeah, so that's the sense in which it's a Heisenberg algebra. It's also a semi-direct product. That means that this guy's act not trivially on it. We don't have to go into that unless people are interested. So it's a big algebra. Yeah. How big is it? It's the following dimension. It has dimension equal to 4 plus d times d minus 1 over 2. It's much bigger. So just to show you how much bigger it is, if you were in 2 dimensions, you know that the conformal group is SL2R times SL2R going in the 2 light-like directions. If I was to put a timelike line in, you know that it breaks it down to just an SL2R along the line. There's no transverse directions. And in this case, this group here, it would preserve the entire left-moving SL2R, plus the right-moving K minus, and the right-moving, where is he? J0 bar. So it preserves 5 out of 6 generators in the 2D case. That's like basically the whole 2D CFT. Okay, so it's a lot of generators.
Is this the Schrödinger algebra?
It's almost the Schrödinger algebra, that's great. Yeah, so it's almost the Schrödinger algebra if you throw away this piece here. So if you throw away this piece here, this is also the symmetries of a non-relativistic CFT 1 dimension lower. And this is related to the fact that if you actually take a light-like line like this, and you did a Fourier transform along this direction, the other direction, you did some sort of null reduction, what you would have is you would have a family of Schrödinger problems that are mapped into each other by the remaining J0 bar. So indeed, you can do a KK reduction, you can basically get a family of Schrödinger problems. That's right. You may be surprised. We've preserved all the KIs, K minus, and K plus. That means we preserved every single special conformal transformation. This is maybe not surprising in hindsight, because you know that what a translation does is a translation moves the origin and fixes infinity. Special conformal transformations are related by inversion, so they just do the opposite. Special conformal transformations move infinity, but fix the origin. When you're in Lorentzian signature, the origin is not a point, it's the light cone, and infinity is not a point, it's scry. So what you've seen is I put a light-like line along the null cone, and then of course, every single translation acts non-trivially. So that's why we've actually preserved every single special conformal transformation. Are there any questions about this? It's like a huge algebra, and now we're going to see what happens if you have this huge algebra. Seeing how that looks. Are we bored, or so I can jump into some stuff? Questions, comments, concerns? I'm seeing a no. Okay. Thank you. Appreciate the vocal response. Okay. So yeah, let's see some abstract results from having such a big algebra. Now, I technically only studied the symmetries of a kinematic line. I didn't actually like say I'm going to put any theory on that line. I haven't actually said what that theory is. Now, mostly in the paper, I'm interested in things that are schematically of the form, take a CFT, S CFT, let's say, not super conformal, just the action of a field theory. I'm interested in defects that are of pinning type. So let's say you just take a local operator and you just integrate it along the line. Yeah. So if you actually do this, you're going to not necessarily preserve all the symmetries I said, right? So in the UV, you're going to have your subgroup of your classical symmetries that were preserved. So that's going to be some subalgebra, this n subscript d, right? I mean, just adding this pinning defect could break some symmetries. Then there could be actual symmetry breaking. So you could go then and you could actually find solutions. You could take a look at correlation functions in the presence of such a defect. And some of them might also just break some of the symmetries, even though it was present in the action. That's symmetry breaking. This is all just still at the classical level. So then even quantum mechanically, there could be quantum effects. Okay. So of course, you know that symmetries can be, for example, marginal, but then they might be quantum mechanically relevant. And then finally, there can be emergent symmetries. So you might go through all this hard work studying something along an RG flow, and then in the IR, you get a whole bunch of magical emergent symmetries. Okay, so there's a whole, if I'm going to ask you, if I gave you any concrete particular problem, you have to study whether or not they're broken in the UV, whether or not the solutions still preserve them, whether or not that's true quantum mechanically, and whether or not things emerge along RG flows. That's fine. In this talk, we'll mostly just focus on 1 and 2. We'll do classical field theory today. I also point out that there's another ambiguity. anytime I do a deformation of a quantum field theory, it raises the question of what do you actually want to flow in, right? So you can do flows. The thing that we almost always flow in is we almost always do RG flows in scale transformations. But you could just as easily have done a RG flow in one of my chiral dilatations, J0 or J0 bar. For example, doing the J0 dilatation or flow is more closely related to the sket or this BFKL. You could do something very exotic. You could go into a random quantum field theory and you could do a flow in chiral. You could do non-relativistic flows. You could also do a flow in chiral transformations on fermions. In most field theories, this wouldn't be very interesting, but in a field theory with a chiral anomaly, this would move you in the space of quantum field theories by changing the theta angle. So you can do flows in anything. And in this case here, two natural ones are this D and J0. Luckily, I'm going to study classical field theory today, and so I'm not going to have to worry about any difficult problems of quantum mechanical effects.
So
Yeah.
Neither of these is an energy associated to X plus. So, like, no, sorry, incoherently stating with. X minus is distinguished here. If I morally want to think about X minus as a quote unquote spatial coordinate that I arrive at by boosting, say, a slightly, take your light-like direction, make it slightly space-like and boost it. I might have thought of X plus as naturally giving me a time. For evolution and associated energy and RG flow.
Yeah, so you're right. Yeah.
But that's neither of these generators, right? That would be P minus maybe?
Yeah, so yeah, my defect is along X plus equals 0. And you're suggesting doing what transfer? You're saying, yes, this direction could be like a time. Is that what you're saying?
Well, you're placing a defect along
Yeah.
X plus equals, right?
Yeah.
Couldn't I imagine some kind of natural Lorentzian time evolution in the other direction?
This direction.
Yeah, that way.
You can do that.
Like a DLCQ type.
Yeah, absolutely. Yeah, you could do that. And then what do you want to do with that?
Just RG flow in that direction if you want.
What do you mean by RG flow in that direction? You mean
Sure.
maybe do one of the chiral dilatations or something like that? Do J0 bar?
Something on. I mean,
yeah.
Here X minus is non-compact, but I could, again in this DLCQ spirit, imagine compactifying it.
Absolutely.
And then considering a periodic defect, yeah. No distance again, but some periodicity condition on that sort of.
Yeah, you definitely could do that. I do have.
I guess it's a question of what you want to study. So
absolutely, yeah. That's actually why I brought this up, just to say that these fixed points are interesting because, for example, if you were a maximally symmetric fixed point, you're interesting for people doing D flows, J0 flows, J0 bar flows. You're interesting for people who do CFT. You're interesting for people who do sket. You're interesting for people who are interested in J0. I do have issues with light cone quantization, of course. I mean, famously, you forget all these massless modes, and that's actually one of the things that makes I erased it. That's one of the things that makes the question of do these things have a good defect Hilbert space very difficult, because you don't actually know how you should foliate spacetime to construct your defect Hilbert space. Yeah. Good news is you don't have to worry about these things. So if you study very simple problems. So what we could do is I'm just going to make everyone a table here. So pretend I did something like this, where I added a local operator to the action, integrated along a line, and pretend that thing had scaling dimension, let's say little delta, and spin j, okay? Then what I can do is I can just compute and see which of the symmetries are preserved. So let me make a table for everyone. P minus, D, M plus minus, K plus, Mij, K minus, sorry, Ki, K minus, and minus I, yeah? So this is like some big table I'm making of all the generators that could possibly be theoretically preserved. Now, if I was to add a scalar, so that's j equals 0. Sorry, the writing here is so small, but it's okay. I'm not going to use this much. If you add it, it's obviously going to preserve P minus. It's going to preserve D if its dimension delta is equal to 1. It's going to break M plus minus and K plus symmetry, and you'll preserve everything else. If you added a delta equals 2 scalar, you're going to preserve this. You're going to break these two guys and keep J0 instead of, and throw out J0 bar. This is just something you just check. You just literally have to brute force it, yeah? You're going to preserve K plus, and you're going to preserve everything else. So you can see already that like a 3 plus 1D scalar, if you just took the 3 plus 1D free scalar, you took a pinning deformation and you integrated it along a line, that you would break M plus minus symmetry and K plus symmetry. For a delta equals 2 scalar, you would preserve the Schrodinger algebra. You preserve everything except this J0 block. So neither of these cases actually preserves this maximal symmetry algebra. There is one that does, is if you add a vector. So if you add something which has delta is equal to, or sorry, J is equal to 1, and delta is equal to 1, then it preserves every single generator of the algebra. So at least at the naive level of the action, if you add dx mu, a mu, and integrate it along the line, you preserve all of these symmetries. It's the only hope that we can think of at the level of pinning field deformations to preserve all the symmetries. Of course, you could still have symmetry breaking in any of these scenarios, and it could be that this option is not viable. And there could still be emergent symmetries. You could add a pinning deformation in the UV, and then you do some RG flow, and in the IR, you have all these symmetries reemerge.
This is like.
Yeah, this would be like a null Wilson line. The null Wilson line is the only hope, at least classically, of preserving all these symmetries at the level of the action. Yeah, and in fact, this fact that the null Wilson line preserves all these symmetries is super important as well. It also means that the null Wilson line is inherently half BPS. Preserves all the R symmetries as well, if you're in like n equals 4. Are there any questions about this? I'm literally just saying like, what are some examples of theories where you can add things to the action and what symmetries are preserved? Amazing. Okay.
So what about non-local operators that cannot be written like that?
Oh yeah, yeah, no clue.
Okay.
Yep, it's a good question. It's a great question. These are just the simplest things. So, but yeah, it's a great question. In fact, it comes back to this point about light ray operators, but maybe we should save that for later. Great. So you can add all of these. You can study all these different things, and then we can ask. So you've still got these pretty big symmetry algebras. I mean, even the free scalar, which breaks M plus minus and K plus symmetry. Sorry, when I call it free scalar, I mean the delta equals 1 free scalar. You still preserve way more symmetries than any usual conformally invariant line. So it's kind of an interesting problem. And so we might ask ourselves, what are correlation functions going to look like in some theories that actually preserve some subset of the symmetries? So let's pretend, I'll write down 3 scenarios for everybody. You could have a scenario where you only preserve P minus, K plus, some linear combination, D plus alpha, M plus minus, of the 2 types of like dilatation generators and their rotations. And then you can show that a scalar operator in the presence of such a line, so a bulk scalar in the presence of such a line, is proportional. It has to look like this. Okay, so it's kind of intuitive, right? This is exactly what you'd expect for a usual 1D CFT. If you put in a line, then it's basically you get 1-point functions, and the 1-point functions are based on the distance to the line. And that's what happens if you only preserve these generators here, some very small minimal subset. Okay, what about for something like a scalar? For the scalar symmetry group, which is much bigger, I'm not going to rewrite it out, it's on the board over there. So a delta equals 1 pinning symmetry, let's call it. You find that the correlation functions take a very curious form. If you put any bulk local operator in the presence of the defect, its 1-point function is necessarily of the form the distance to the shockwave plane, so this is x plus to the delta, plus, this is a delta function, delta, x plus, and then some homogeneous function in the perpendicular direction. Let me unpack this for you. So this is basically saying, if you took a bulk local operator, you have the line like this, and then you have some bulk local operator. Remember that this is the x plus equals 0 direction, and the x plus equals 0 plane is sticking out the board like this. This is basically saying you can either measure how far you are from this whole shockwave plane, or you can be exactly on the shockwave plane, and then you're basically, when you restrict yourself to just that shockwave plane, your correlation functions take some form where this is a homogeneous function of degree 0. Okay, so that's just some weird thing. So basically, again, you put in a line of charge, but for some reason you distinguish this entire shockwave plane. So the second you study null line defects, you're basically forced to study planar defects. It's very strange behavior. But maybe this is intuitive, right? Because if everyone remembers their classical E&M class, their usual electromagnetism class, they remember that if you took a charged particle, and you started boosting it, its field profile got flatter and flatter. And when you ultra boosted it, that the field profile presumably becomes very flat. And that's the shockwave plane.
So just to make sure I understand what, yeah, I haven't thought about the story at all.
Yeah.
So you're inserting you're inserting a local operator on the line.
Away from the line.
Away from the line in the
Correct.
presence with the Lagrangian perturbed by your pin, by your.
That's right. By some symmetries that are matched up. Yeah.
Gotcha.
You see, it has to have this form. Then we could do one more example. You could say, what about this maximal, right? That's the most interesting one. Maximal symmetry. And for maximal symmetry, you find the following. You find that for any operator, spinning or not, the 1-point function must be 0. Contact terms, but 0. So that means that if you ever have a maximally symmetric null line, all of its 1-point functions must be 0. Now, I can already see somebody says, well, but that doesn't make sense because I know that I can just OPE any collection of local operators down to one local operator, and then use its 1-point functions in the presence of a line, and then everything must be 0. So then you say, oh, they don't exist. However, you should be careful because in Lorentzian signature, these two local operators on different sides of the line, let's say on different sides of x plus equals 0, cannot actually be OPE'd into one operator. So there can be information actually in the 2-point function. You can have all the 1-point functions be 0, but the line does not have to be trivial. Because this OPE that connects these two does not converge.
How about the identity?
The identity? Oh, sorry. The identity is still 1. Yeah. That's that. There you go. Okay?
So I actually a bit confused about the second case. So
Yeah.
when I think about the infinitesimal version of this,
Yeah. What do you mean infinitesimal?
like you insert this non-integral scalars in the exponent, I just kind of expand that.
Yeah.
It's kind of like a 2-point function of one local operator and one non-integral scalar.
Yeah.
But I thought in the CFT that's just 0.
You want to say that's 0 because it's integrated along the line?
Yeah.
And that the light ray operators annihilate the vacuum?
Yeah.
Absolutely. However, this is delta equals 1, j equals 0. And you know that the light ray transform doesn't converge for delta plus j, equal to 1.
Okay, so this scalar you start with. Is it a CFT local operator?
Yeah.
Okay.
Yeah, it's just the light ray
It's
transform.
no complex.
It's like literally just the free scalar that like evades this problem. Yeah. So yeah, you can have your 1-point functions of everything not the identity be 0 and still have something interesting. And in fact, in the paper, we argue that we do it mostly for scalars, but you can also do it for non-scalars, that if you have any theory whatsoever, and it has a line in it, and that line is infinite and maximally symmetric, that all of its 1-point functions must vanish. And the 2-point functions of two operators, let me write them as if they were scalars. Okay, the 2-point functions of those operators must take the following form: delta 1, delta 2, t, s1 is 2. I'll explain this in a second. x1, 2 delta 1. So 2-point functions in the presence of the line must take the form of standard 2-point functions, but with this one function here. And all this function is this function is a possible change. It's a possible discontinuity across the shockwave plane. So our claim is that all maximally symmetric defects, if they exist, all of the physics in them is contained in the shockwave plane. There's people who actually study physics in an example of like shockwave gluon backgrounds or something like this, and you can see they basically can compute this function. We didn't know about that when we wrote the paper, although they're not studying CFTs, they're studying actual QFTs. So yeah, all the physics of a maximally symmetric line is in this discontinuity, and even in non-maximally symmetric cases, there's still this distinguished shockwave plane. I'm doing horribly on time. I could talk about some examples, I could talk about test functions, or I could talk about the null Wilson line. What do people care about? Who wants to hear about the free scalar?
Me.
Yes.
I need an example.
Yes, okay, sorry for, wait, what are you talking about? This is every example.
Yes, I
No.
need one more.
Okay. Great, yeah, so let's stop all this highfalutin solving of word identities, and let's do the easiest example in the world. Let's take a look at the free scalar, yeah? So I have S equals 1/2. Can you believe I'm writing down the action of the free scalar? Doc, it's like pretty bold. So Bx minus phi 0x minus, yeah? Okay, let's do some free field theory. So we take a look at the equations of motion, yeah? The equations of motion are now modified to d squared phi is equal to h delta x plus delta squared x. Good, great. Then what we do is we do the thing that we would do in any class. We would solve the thing. It's a free field theory, so we may as well just look for the classical solutions. The classical solutions will just be the 1-point function. Okay, so now we have two choices. We solve it by standard methods, so we just like solve the Green's problem. And we have two options. We can find the causal solution by using the retarded propagator. Okay. You could also think of this as what you would get if you did the informalism, okay, or a Keldysh-Schreiner formalism. And you find that the correlation function, the 1-point function, looks like this. I'll explain this notation in a second. So this is just by using the retarded Green's function. Or you could solve this PDE either by Fourier transform or by using the Feynman propagator, and you get a thing that I call the shockwave solution. Okay, and that takes this form, phi s of x is equal to h delta x plus, and then Feynman propagator in 2D. Okay, makes sense? You can very clearly see that this satisfies this thing here. Remember, d squared is equal to d plus, d minus, plus di squared, yeah? So you can very clearly see this creature obviously satisfies it. It's d minus hits it, vanishes, but then di hits it, and it just turns into delta x plus, and the delta function acting on the Feynman propagator. This guy's more mysterious. You'll notice that I didn't put these theta of x plus, I called them theta of scare quotes x plus. What is theta of scare quotes of x plus? Theta of scare quotes x plus is something that naturally appears when you actually solve the problem. And it relates to the fact, so let me tell you what it is. Theta of scare quotes x plus is equal to x plus over 2 plus xi squared over 2x plus. And you take a look at this quantity and you say, oh, well, Justin, this thing is x plus over 2 times 1 plus xi squared over x plus squared. And so you say, it's very clearly just theta of x plus because it's x plus times a totally positive function. You say, well, then why didn't you just call it theta of x plus? Well, it's because it's very important that anytime you have a theta function, theta of x, it is not equal to theta of x y squared. They're equal every time x is greater than 0, so it has the same support as x plus, but they differ exactly on how they look at the boundary, right? These things have different distributional behavior at the boundary. And this is super important because only with these terms do you actually satisfy the equations of motion. You can check by using a nice form of a regularized theta function that only this solution matched it. Obviously, if you erase these scare quotes, it wouldn't work anymore because you just hit it with this thing and it would just vanish. Game over. So this is the solution. You can think of this solution in a whole bunch of different ways. I just want to say it's not like something that's just made up to solve the equations of motion. Okay. When you think of this, this is also what would happen if you turned on the defect adiabatically. So you pretended in the arbitrary past it was off, and then you slowly turned it on in time. You will recover this solution. This quantity is also natural if you stare very closely at what points in space are actually in causal contact with your light. It's kind of intuitive, right? You have a defect like this. You're looking at the retarded solution. You know that it has to have this 1 over x plus scaling, and it's just basically saying they die off in time on this side of the defect, with some strange singular behavior as you approach the line. Essentially what this thing is doing, another way of saying it, is that there are points in the shockwave plane which are not actually in causal contact with the line. So this theta function is basically saying everything to this side of the line is in causal contact with it. But if you're right on the shockwave plane, you're not. And that's also another way to think about this theta function is doing. Oh, doing terrible on time. Okay, If you also look, unfortunately, I erased it. These solutions are exactly of the form that I predicted using just the general analysis, right? Because I promised you they would be like 1 over x plus to the delta. So this is the 1 over x plus behavior. This is just some coefficient that is the right causal structure. So it actually has no scaling behavior. And this creature here is a shock wave times a homogeneous function of dimension 0. Because in 2 dimensions, it is the Green's function is, of course, some log. Say mu squared xi squared. Yeah. So it has exactly the behavior that you would. Okay, so I've done a bad job on time. So let's see. Let me just answer some random questions that I expect people would now have if they had to start this problem. So the first thing you might wonder is, does it match the spacelike and timelike limits? So if I had put in a timelike line or a spacelike line and I arbitrarily boosted them, would it match these solutions? And the answer is yes, it does. You have to be very careful though, because when you actually take the timelike or spacelike limit or the boost, this coefficient h gets rescaled, right? This thing does not behave nicely under m plus minus. And so you'll find that what you actually have to do is you have to rescale h when you take this boosted limit. This leads to maybe a result that I'll summarize like this. Any ultraboosted conformal defect, right? So you might say, I might be able to obtain some class of null defects by ultraboosting timelike or spacelike defects. Any ultraboosted conformal defect satisfies one of the following things. It either has a vanishing one-point function, okay? It is part of a defect conformal manifold. Defect conformal manifold. That's what's happening in this free scalar case. Or 3, it is kinematically equivalent to a null Wilson line. Although we also know that this is just a subset of option. And further note, okay, so all of these 3 points are clear, because what I'm basically saying is when you do a big boost, you're basically going to crush this coefficient up front. And so when you crush that coefficient up front, it either means that you had a vanishing one-point function in the limit, or you had to be a part of a defect conformal manifold where you could rescale the coupling with your boost and have a nice finite limit. That's what happens in this case of the free scalar.
Can you actually think of any of the null lines as coming? I mean, couldn't you have taken any null line, make it slightly timelike, and then boost it all the way to timelike?
So you're saying take the null line.
I mean, are they all infinite boosts of something that's not null?
All null lines.
Yeah. Or are there some null cases that you can't get from?
Well, that is indeed the point of this theorem. The point of this theorem is saying any one that is of that case, which we already think of as being the ones that probably exist, the super boosted limit of timelike things, has to either have vanishing one-point function, be a part of a defect conformal manifold, or there exists some just intrinsically null things which are not of this form. For example, I would actually expect that if these exponentials of these light ray operators exist, they're probably of this form. Because
of the form that they can't be obtained.
That they can't be obtained as a super boosted limit. I'm just speculating this. Maybe I shouldn't have said that since it's recorded and going on YouTube. Somebody will point at it in 50 years and make fun of me. So that's a random fact. Well, it's not so random. You just solve it. If I had more time, I would have solved it in front of everybody here. It's really quite a nightmare showing that this theta function emerges when you take this ultra boosted limit. There's a whole appendix of distributional garbage that I had to go through to prove that. You may also notice something else. Look at this shockwave solution. I said to you that if a free scalar exists, one of the things that the symmetries it has to preserve this D symmetry. Yeah? But this creature here, the shockwave solution, he has an arbitrary scale, mu. And so you say, okay, that means that you've spontaneously broken your scale symmetry, maybe. Yeah, that turns out actually not to be the case. It turns out not to be the case for some technical reason, which, definitely not gonna have time to go into. But my claim is that if you're in a usual quantum field theory described by the Lightlike series, Lorentzian quantum field theory, let's say, it's well known that correlation functions are not actually functions, they're distributions, yeah? They're distributions on some space of test functions. And in particular, we usually think of them as being dual to the space of Schwartz distributions, or sorry, Schwartz functions. So these are functions which fall off sufficiently fast at infinity. In fact, it is claimed in a paper of Kravchuk, Chow, and Richkov that if you take a look at correlation functions of local operators in any quantum field theory or any CFT or any quantum field theory which is UV complete, that they are always distributions on this space of test functions. However, they only focus on local operators. And one of the things that we show in the paper is that if you take a look at quantum field theories, Lorentzian quantum field theories with a null defect, that you have to slightly shrink your space of test functions. So you want to study instead some space S null inside the space of Schwartz test functions. And it'll consist of all Schwartz test functions, F, such that if you integrate them over all of space times delta of x plus, that you get 0. Now, this may seem like an obscure condition, but it's actually very physically motivated. We motivate it from some physical principles of removing divergences. But I don't have time to go into it. But this condition is extremely strong, as it turns out. Well, it's not extremely strong. I mean, there's still things in the space. But in particular, one of the things it means is that if you have any distribution, because all of your test functions, when integrated against delta x plus, have to be 0, it means that if you have any distribution, any correlation function, and that correlation function is proportional to a delta function, it means that this thing is functionally 0 or distributionally 0. It's essentially equivalent to 0. Okay, because if you took it and you integrated it times any test function, this thing is 0. Right? Now, yeah, what does this mean? Well, this has a really important consequence. The important consequence of this is that this term here is actually independent of scale. Because if you actually see, okay, pretend I change the scale, mu d mu, of log mu squared xi, delta x plus, you see that it's just, the change in the scale is just proportional to some constant times delta x plus. So it means that if you change this arbitrary scale, which emerged in this log, it means that the correlation functions actually don't see it. This may seem obscure, but this happens in usual conformal field theory. This happens in usual conformal field theory because if you take a 2-point function of marginal operators in even dimensions, and you go to momentum space, the correlation function is proportional to, I'll end after this. It's proportional to PD log mu squared E squared. Now you can see this from, you could imagine you have marginal operators in D dimensions. So you know how the thing scales. You do a Fourier transform, you can see it's proportional to this log. And you can read the paper of Gomes, Hien, Komorgodsky, Schwimmer, Seiberg, and Thiessen, and they basically point out, okay, this is how the 2-point function of two marginal local operators looks in momentum space in even dimensions in the standard conformal field theory. But why is this not a problem? Well, because if you take mu d mu of this thing, you see that what comes out over here is it's something that's polynomial in P. But a polynomial in P is just a pure contact term. So you can ignore it. And what I'm basically saying here is what this space of test functions is it's some modification of this of what contact terms look like in the presence of a null line. This does not happen for a timelike line or a spacelike. I have the condition written out here, but yeah, we probably shouldn't go into it. So it's not obscure to change the space of test functions. It's changing what you mean. It's changing your conformal anomaly. It's changing what you mean by a contact term. Yeah, so I'll end here in one sec. I'll just say one few word about the Leonard-Richard potential and the null-Wilson line. So you might say, why did I go into all this junk about contact terms, test functions, like who cares? It turns out that there's been a problem that was worked on, well, very long time ago, is the problem of how do you make sense of a massless charged particle? So what would happen in the literature is that people would go and they would study the potential. So they'd say, okay, I'm going to study a massive charged particle. And it's your unambiguous chart problem, right? From your classical ENM. And people would go and they'd work in Lorentz gauge. And they'd say, okay, in Lorentz gauge, I take some source, yeah. And I say, okay, box A mu is equal to J mu. They would take that timelike source, they would solve for A mu, and then they'd super boost the solution. And what they would find when they super boosted the solution is they'd find that the solution actually didn't make sense. They'd get some A mu, I'll call it like limit, maybe I'll call it A lim, yeah. And they'd find that the limiting solution didn't actually solve the Lorentz gauge for the ultraboosted current and gave some gibberish field strength. And then they would say, well, it doesn't matter. I mean, Jakif has some paper on this from like the 90s. They'd say, it doesn't really matter because we know the gauge potentials aren't physical. What really matters is F mu. And they'd solve instead for F mu, and they would super boost that, and they would find that they get the right shockwave F mu. It would be proportional to delta x plus, makes perfect sense. And they say, it's just because the gauge potential it's not a real physical thing. Who cares? Lorentz gauge is just a storytelling device, right? No such thing as a gauge theory. But the point is that the whole point of this 3 + 1D free scalar is when you're working in Lorentz gauge, the linear weight chart problem working in Lorentz gauge is just the 3 + 1D free scalar, right? The 3 + 1D scalar is just this problem. And what we're saying is that the solution to this problem of ultra boosting the gauge potential in classical ENM is just resolved by the space of test functions. So it's kind of a result in classical electromagnetism. People have known for a very long time that if you ultra boost the field strength, you get some sort of shockwave solution. But they never knew how to make sense of what do you do when you ultra boost the gauge potential. And I'm telling you the solution to that is you can ultra boost the solution. And even in these papers, people are saying, oh, well, the limit doesn't actually make sense in the space of Schwartz distributions. And I'm saying that the answer is, that's true. You weren't supposed to take the limit in the space of Schwartz distributions. You're supposed to take it in this space called S null, which are functions which satisfy this condition. Then the limit makes sense. It limits to a well-defined potential. It looks just like the free scalar things, except these creatures here become A minus and A minus. And then you can take derivatives of these creatures, and you find that it recovers the usual shockwave. So it's sort of the answer to, I mean, I guess people could have solved this for a long time, and people don't really care because they don't care about the field strength. The nice point is it's a nice result in classical ENM, and we were forced to solve it because the 3 + 1D free scalar is just this problem. It's no longer, you can't just say, it's not physical, it's not physical, who cares? So that's what happens when you take a massless free scalar. Oh yeah, and then one more punchline. I said that if anything had a hope of preserving maximal symmetry, it was this null Wilson line because it's the only thing that preserved it all. Oh yeah, you can also just compute F mu. And when you see F mu is proportional to delta x plus, and that means that the whole solution is supported on the shockwave plane. And K plus symmetry moves the plane. So the solution actually spontaneously breaks conformal symmetry. So even our one hope was this null Wilson line. And he also broke the maximal conformal symmetry. So we actually don't know a single example of a quantum field theory with a maximally symmetric null defect. And it's possible that they just don't exist. But yeah, I know that was a lot at the very end. So thanks everyone for listening. And I would be really, really happy to take questions because I know I blazed through this. So. Sorry.
Just a random comment in the question. The random comment is, I think this last discussion was really interesting about the potentials. It reminds me of, I think, things people were doing in the study of asymptotic symmetries, four dimensions, where I can't remember for sure, but I thought for the Maxwell case they had some expression. There's a lot of patching going on at the celestial sphere, and were there expressions for A plus A minus there, or? I thought there was some kind of superlocal, hyperlocal, I forgot what they called it, collapse at Stony, which had the same flavor as your theta quote unquote x plus.
Right. Okay. So I don't know about superlocal and hyperlocal. I mean, I can say that there's that these solutions satisfy. this solution here satisfies your antipodal matching and everything like that. And actually, curiously, to this point, these two solutions, they produce the same FU nu. So they are actually gauge equivalent, which is kind of funny because it means that the retarded solution, also the anti-retarded solution, and the advanced solution, and then the shockwave solution, all actually produce the same field strength, so they're actually gauge equivalent. But they these are also the solutions in Lorentz gauge. So it actually means that the thing that relates them is a harmonic function. And since it's a harmonic function, like the harmonic function is basically saying that what that harmonic function is doing is it's just kind of changing the profile at scry, right? Because it's something that's invisible to like this solution is privileged as the thing that comes from the Fourier transform.
Yeah.
But the Fourier, yeah.
That change of profile is right, I think, is the memory effect.
That's right. Yeah, I mean, they have different memory, exactly.
Yeah.
Yeah.
So do you think this could be useful then for quantization, for talking about things like the S matrix? And so in QED, the problem was sort of solved by Coolidge and Pathev in some form.
Yeah.
We interpreted it, I think, in terms of dressing with open Wilson lines.
Yeah.
But there's no analog of that for gravity or QCD at the moment.
Yeah.
Do you think this could potentially help in the conformal case?
Well, yeah, I mean, I do have comments on that, but not for you two.
Yeah, maybe afterwards.
Oh, was there another question? Or?
So so if you had a dream around this that could be solved, what would be the dream result from that you would like to see from this approach?
So from a pure abstract nonsense point of view, I would love to know if there exists maximally symmetric defects. I suspect that's not the case. There is a sense in which the null Wilson line is maximally symmetric, but we didn't get into that. You have to go to the Lorentzian cylinder to really understand that point of view. I didn't have time for it. So that would just be one abstract existence thing. On a more practical side, I would love to know how this story relates to this sketch, this BFKL, because these maximally symmetric endpoints, or not even the maximally symmetric, but this huge symmetry algebra is one. I think one reason why it's so big is because these fixed points are like simultaneously the limits of conformal fixed points, but they're also like simultaneously sket fixed points. And I think somehow, yeah, it should be useful to both communities. I'd love to understand how that's related. Now, let me say one final third thing. This could be either a practical problem or a theoretical problem. Is I would love to know if you could exponentiate a light ray operator. Because in principle, that's what I said one of the motivations of this thing was to find out if light ray operators are just a mathematical trick, it's just some integral transform on spaces of correlation functions, or is it some actual physical useful thing? Yeah, like in principle, you would think the ANIC is super physical, right? It's something that exists in principle in every quantum field theory. It's the stress tensor integrated along a null line. It's important for proving monotonicity theorems. It measures energy. It's an idealized calorimeter. But can you actually exponentiate it and produce a finite observable? I don't know. And that would be like the universal observable that every quantum field theory has, the ideal calorimeter, right? It's kind of showing that would be very interesting. Problem is that T mu nu is not marginal. It's not even relevant, right? It's irrelevant. So you would either need infinitely many counterterms. But maybe because the symmetry algebra is so big, you can constrain all these counterterms. I don't know.
It has a kind of TT bar like flavor.
Sure.
Maybe that's somehow the right generalization of TT bar above 2 dimensions.
Sure, I'd love that. But yeah. Sorry for the disorienting talk. Are there any other questions, comments, concerns?
Should I be worried about these distributional issues when I insert timelike and spacelike defects?
Yes and no. Timelike, so anytime you're in Lorentzian quantum field theory, you should actually be quite concerned about the fact that correlation functions are not functions, that they're distributions. For timelike and spacelike, you can actually prove that this S null condition is not necessary and Schwartz distributions are good enough. Well, let me show you just one quick picture why. The quick picture why is because you're trying to find out if you can actually invert certain like PDEs, like box inverse, yeah? And the point is that if that thing's actually invertible, there's usually some integral involved, and that integral is going to blow up at its endpoints. You have a timelike defect, and you have some point way in the future of that defect. Okay, it's in causal contact with everything in this past code. And what you'll see is that because of the Schwartz condition, you're not actually going to have any issues because functions basically die really far in the past cone. Exactly. And then when you're on the null line, this cone is along the line itself. And what this thing condition is actually doing is it's just deleting this line. It's basically saying, okay, the Schwartz functions are good enough to prevent divergences, but you also have to make sure that you've kind of picked up a humongous contact term from integrating along the line itself. Great question. Yeah. Okay.
There are no more questions. Let's thank Justin again.